Good morning, students. Welcome to your chemistry class. Let us further discuss the chapter Chemical Bonding and Molecular Structure. In our today's class, we are going to discuss valence bond theory. In this, we are going to discuss its main postulates, concept of hybridization, examples of valence bond theory. Now, first of all, we should know that which scientist has proposed valence bond theory. So, the valence bond theory was proposed by Hitler and London to explain the formation of covalent bond quantitatively using quantum mechanics. Later on, this theory was improved by Linus Pauling by introducing the concept of hybridization. The main postulates of valence bond theory are: a covalent bond is formed by the overlapping of two half-filled valence atomic orbitals of two different atoms. So if there are two different atoms, the orbitals will be consisting of electrons and they are going to overlap with each other, and then they are going to form a bond. The electrons in the overlapping orbitals get paired and confined between the nuclei of two atoms. So initially, supposing, let us consider hydrogen atom. Hydrogen atom have one electron, they overlap with each other, and then we can say that the electron that are being paired up, they are confined between the nuclei of the two atoms, and this give rise to covalent bond formation. The electron density between two bonded atoms increases due to overlapping. So this is the one factor on which stability depends. Greater the extent of overlapping, stronger is the bond form. Next, in which direction is the overlapping taking place? That's also very important. So the direction of the covalent bond is along the region of overlapping of the atomic orbitals. That is, covalent bond is directional. There are two types of covalent bonds based on the pattern of overlapping, that is sigma bond and pi bond. Now, what is a sigma bond? Covalent bond formed due to overlapping of atomic orbital along the internucleus axis. That's known as sigma bond. It is a stronger bond and cylindrically symmetrical. So, when the overlapping is along the axis, then this gives rise to sigma bond. And they are of different types. Let us do it one by one. So depending on the types of orbitals overlapping, the sigma bond is divided into following types, that is SS overlap, SP overlap, and PZ overlap. These are the orbitals given to you. We have already done this in our previous chapter. So S orbital when overlaps with S orbital, let us have a look at how the sigma bond will be formed. Since both S orbitals are symmetrical in shape, the sigma bond is represented in such a way. Now next, if the S orbital is overlapping with the dumbbell-shaped orbital of the P, then the sigma bond is represented like this. When two P orbitals overlap together, then the sigma bond is represented in such a way. The next bond is pi bond. The covalent bond formed by sidewise overlapping of atomic orbitals is called pi bond. So you can have a look here that it is a sidewise overlapping. It is not end-to-end overlapping. In this bond, the electron density is present above and below the internuclear axis. It is relatively weaker since the electrons are not strongly attracted by the nuclei of bonding. So here one example has been given to you that the 2p first and second are fully filled and one orbital of the p is half filled in one case and in the other as well. So they both are going to overlap with each other and this will give rise to pp overlapping. Now let us consider the formation of oxygen molecule. In this, as you know that oxygen have atomic number 8. So it is 1s2, 2s2, 2p4. Now there are two p orbitals half filled in one oxygen atom and there are two p orbitals half filled in the another. So what is going to happen is py is going to combine with the other py and pz is going to combine with the other pz to give rise to oxygen molecules. We can also represent the structure in such a way. We know that oxygen molecules half filled orbitals are py, pz. So that are being drawn. Along the axis, PZ overlapping will take place. So this will give rise to sigma bond. And here PY are going to do the overlapping and this will give rise to pi bond formation. That is a sidewise overlap that takes place.
Now the next topic that we are supposed to do is concept of hybridization.
Now why hybridization came into consideration? Now, if I take an example of carbon with atomic number 7, the electronic configuration is 1s2, 2s2, 2p2. So, the arrangement that carbon should show should be 2s fully filled and there should be 2 electrons in the p orbital. Okay. So, as we were seeing in the case of oxygen, that is the bond was formed between py, py and pz, pz. So, the valency here is 2 because 2 bonds are formed. But in organic compounds, we have observed that carbon has valency 4. Now, why this might be happening? This might be happening due to excited state of that carbon atom. So, in excitation state, what happened? That one electron from the 2s orbital jumps in the 2p orbital and there are total of 4 half-filled orbitals present which can take part in the bond formation. Now, these will be of the similar energy that are being formed. Okay. And this concept has given rise to hybridization. Now, what is hybridization? The process of mixing of atomic orbitals of nearly same energy to form a set of new equivalent orbitals is termed as hybridization. Okay. So, in our previous case, as in this case of carbon, 2s and 2p, they have mixed up and they have formed orbitals of equal energy. Now, how to predict the shapes of orbitals based on hybridization? Let us do it one by one. Supposing the number of atomic orbitals involved in hybridization is 2. That means one s orbital and one p orbital. So, the number of hybrid orbitals will be the combination of these two and it is 2 in number. Now, the shape of molecules of the sp hybridized molecule will be linear and the angle will be 180 degree. And the examples are as follow, like BCl2, BEF2, ZnCl2, HgCl2, C2H2, that is ethine. Likewise, they all show linear structure. So for sp hybridization, let us take an example of BeF2. The ground state and excited state of beryllium atom is given to you. That means in the valence shell of beryllium, there are 2 electrons. Now in the excited state, the electron gets excited to the p orbital and these 2 orbitals s and p, they get mixed up and this gives rise to sp hybridization. And the structure is in front of you, that how the orbitals are going to overlap, and this gives rise to the linear structure of BeF2 which has an angle of 180 degrees. The next is that when the number of orbitals are 3 in number, that means first the s orbital, then 2 p orbitals combined together, this will give rise to 3 hybrid orbitals, and in this case the shape of the molecule will be plane triangular, or we can say trigonal planar, and the angle will be 120 degrees, and these are some of the examples. Now for sp2 hybridization, let us take an example of BF3. In this, boron is having the electronic configuration in the ground state as 1s2, 2s2, 2px1. That has been represented in front of you, that is the valence shell. 2s is having 2 electrons and 2p is having 1 electron. In the excited state, the electron from the s orbital gets excited to p orbital and this gives rise to hybridization. That is, the atomic orbitals all come to the same energy and then the overlapping takes place. And the structure of BF3 is trigonal planar, that is 120 degree angle. Now when 4 orbitals are involved in hybridization, then the hybridization is sp3 type and the shape of the molecule is tetrahedral and the angle is 109 degrees 28 minutes. The example in such cases are CH4, CCl4, SiCl4, ammonium ion, ClO4 minus ion. Now you are already familiar with the structure of CH4, that is methane, that has a tetrahedral structure. But let us take some other examples in which the shape of the molecule is tetrahedral, but there are lone pairs also present. First example in sp3 hybridization is of ammonia, that is NH3. In this, what happens at the ground state of nitrogen atom is having 2s filled and there are 3 electrons in the 2p orbital. This all together forms sp3 hybridization. Since there are 3 hydrogens, so therefore we are having that 3 unpaired electrons and the overlapping will take place and this will give rise to bond formation. And the 2s orbital which is filled in this case will be remaining as lone pair. So the geometry is tetrahedral, but the structure is trigonal planar in this case because there is lone pair also present. Similarly, when we consider water molecule, in this the central atom is oxygen and the atomic number of oxygen is 8. So it is 1s2, 2s2, 2p4. But when we do the hybridization, that comes out to be sp3 hybridized, because for the water molecule to form a bond, two half-filled orbitals should be present. So that is already present in the 2p orbital of oxygen. So the remaining filled orbital, that are paired electrons, the orbitals in which pair electrons are present, they will be there as a lone pair in the structure. Okay, the pair of electron that do not take part in the bond formation. Now next, if supposing there are 4 orbitals, but in the 4 orbitals the combination is dsp2, that means 1 d orbital, 1 s orbital and 2 p orbitals are combining, then the shape is not tetrahedral but the shape is square planar, and the angle in square planar is 90°, and mostly coordination complexes are having dsp2 hybridization and angle of 90°, and they show the shape of square planar. Now, if the number of orbitals are 5, then there are two possibilities. It will be either dsp3 or it will be sp3d. Now, in this, since the number of hybrid orbitals are 5, the shape, or we can say the geometry, will be trigonal bipyramidal, and the example of such geometry is PCl5 or PF5, and the angles are 2. The equatorial ones, the bond which are in equatorial plane, they will be showing the angle of 120°, and the axial one with the equatorial, they are going to show the angle of 90°. So let us take one example to understand this. sp3d hybridization in PCl5 molecule. So when we talk about phosphorus, the atomic number of phosphorus is 15. So the valence shell configuration will be 3s2, 3p3. Now what happened, that one of the electrons in the s orbital get excited and it jumps to the d orbital because it want to accommodate 5 chlorine atoms. So 5 orbitals are having singly filled electrons, and the hybridization comes out to be sp3d hybridization, and the shape is trigonal bipyramidal. Now if 6 atomic orbitals are present, then the hybridization can be either d2sp3 or sp3d2. Since 6 hybrid orbitals are present, so therefore the geometry is octahedral, and the example is SF6 with each angle of 90°. So if there are 7 orbitals taking part in the hybridization, that means the orbitals, if it is d3sp3 or it can be sp3d3, then the geometry will be pentagonal bipyramidal, and the example we can take is of IF7. So IF7 shows sp3d2 hybridization. Iodine atom has valence shell configuration in ground state as 5s2, 5p5. So one unpaired electron is present in the case of iodine in the ground state. But in the excited state, when the orbitals mix together, in that case, the electrons from 5s and 5p, which are paired, they will be going to be excited to the 5d orbital. And this gives rise to sp3d3 hybridization, and the shape of the molecule here will be pentagonal bipyramidal. Now let us do formula to calculate number of orbitals involved in hybridization. Now the formula is H equals to plus half, that is 1 by 2, V plus M minus C plus A. Now what are these? So let us do it one by one. H is the number of orbitals involved in hybridization. V is the valence electrons of the central atom. Supposing the central atom is chlorine, then the valence electron in chlorine is 7. M is the number of monovalent atoms linked with central atom. Supposing it is ClF5, that means the monovalent atoms linked to chlorine is 5. C is the charge on the cation.
A is the charge on the anion.
So if we substitute all these values in this formula, then we are going to get the number. So if the number comes out to be 2, then it will be Sp, and if it is 3, then Sp2, and so on. So this was all for today, students. Thank you so much.